This assessment asks us to use bond dissociation energies to calculate an equilibrium constant of the reaction shown. Let's quickly discuss how we're going to do it. Well, we know that we can calculate KEQ if we calculate delta G, and we can get delta G from delta H minus T delta S. This reaction is two molecules going to two molecules, so we know that delta S is approximately 0, or at least that's the value we're going to use for this. What that means then is to get delta G, we only need to get delta H. Delta H can be obtained using bond dissociation energies. Now, three of the bond dissociation energies that we need are pretty straightforward, present in the table. So the allylic CH, as you can see, I've written up here, is 87 kilocalories per mole. So it takes 87 kilocalories to break that bond. The chlorine-chlorine bond dissociation energy is 58 kilocalories per mole. The HCl bond dissociation energy is 103 kilocalories per mole. And that leaves the carbon-chlorine bond here that is allylic. Now, if you look at the bond dissociation energy table, there's not one present for the allylic carbon-chlorine bond. But let me show you how we can estimate this. And if you estimate it slightly differently, that's probably okay as long as the general idea works out. You might get slightly different numbers, and that's probably okay. Now, if we look at this carbon, the carbon-chlorine here, this is a primary carbon, and so we might be tempted to use 81. But notice up here, the primary CH was 98. The allylic CH was 87. So being allylic takes a primary down from 98 to 87 in the case of the carbon-hydrogen bond. It may not make the same magnitude of difference, but what it tells us is that the allylic carbon-chlorine bond should be lower than the primary carbon-chlorine bond. If we assume that it's a difference of 11, then we could use a number like 70 kilocalories per mole here. Now again, maybe 70 is not the perfect number for this, but we know it's going to be less than 81. We'll solve the problem using 70. We can take the amount of energy we put in to break the bonds and subtract from it the amount of energy that we form the bonds with, and that's going to give us a value of negative 28. Now keep in mind that negative 28 kilocalories per mole is equal to both delta H and delta G, because entropy, delta S, was 0. This allows us then to plug into this equation, which we'll do in this space here. KEQ is going to be equal to E to the negative 28 over 0.001987, the value for R, 298, the value for temperature. If we do this, we get a KEQ that is 3.36 times 10 to the 20. So a highly favorable reaction, which makes sense based on a highly exothermic or exergonic process.